Hello, everyone. We're going to talk about Hess's law, the law of heat summation in chemistry. So, Hess's law is a really handy tool in chemistry that we can use to find the heats of reactions. For instance, sometimes it's hard to measure the enthalpy change for a reaction because sometimes that reaction might be really slow. Or you might not want to, let's say, destroy the thing that you're working with in order to find out the heat of forming that product, or the heat that's involved in destroying that substance. Okay, so I'm going to start with an example of, let's say, taking a piece of charcoal, graphite, and turning that into diamond. All right, how much heat would be involved in making that happen? And before that, I'm just giving you this. You might want to write this down. Hess's law allows us to calculate the heat of a reaction from known enthalpy changes of two or more reactions. In other words, you can go to, let's say, a table somewhere, like a chemistry handbook or something like that, and find the heats of reactions for some reactions that chemists have already observed and measured these changes. You can take that information and sum up the reactions in order to find the heat of reaction for something that you care about. All right, in other words, let's try this first problem where we're going to take a charcoal and turn it into diamond. Okay? Maybe you've heard of this before, but diamonds are actually made by compressing graphite and adding energy to graphite. Graphite being like charcoal. Okay, usually diamonds are formed in the earth where tectonic plates are rubbing together. That would be a lot of energy, a lot of compression. Another place that diamonds are created are like when meteors strike the earth at high velocity. There's a lot of energy that's involved there, and high compression. So anyway, you might have heard of being able to make diamonds out of graphite or out of charcoal. Anyway, so I've written this little chemical equation here where we're changing graphite into diamond, and I want to find the change in enthalpy there. You might suspect that the change in enthalpy should be positive because you can imagine that it's going to take energy in order to make this happen. So that system is going to have to take on a bunch of energy, and you're going to rearrange the atoms of carbon into diamond form. All right, well, let me show you something. Okay, first off, believe it or not, you can burn a diamond. And it has been done, and the energy has been measured to make that happen. You can imagine that was an expensive reaction. But anyway, yeah, you can take diamond and combine it with oxygen to make carbon dioxide. And the energy that comes off would be this many kilojoules per mole of carbon that's in the diamond form. And the same, of course, can be done with graphite. In other words, that's charcoal. Anytime you've ever worked with a charcoal grill, you've done this reaction where you take graphite, charcoal, and burn it in oxygen to make carbon dioxide. This amount of heat would be given off by that reaction. Okay, Hess's law says that we can sum up these reactions to come up with this reaction. But there's something that we need to do first, okay? You'll notice that in these two reactions that I gave you, we're starting with diamond in the first reaction, and we're starting with graphite in the second reaction. But in the reaction that I care about, we start with graphite as a reactant, and we end with diamond as a product. All right, what I'm going to do is I'm going to rearrange this reaction here with the diamond. And then I'm going to show you how we can then add one reaction to the other reaction to get this product reaction or this final reaction. Okay? So, first thing I'm going to do is I'm going to take the diamond reaction and I'm going to reverse it. Okay? First, I'll just talk this through and then I'll write it down. If I take this reaction and reverse it, I will start with CO2 and end with carbon in the diamond form and oxygen. And this change in enthalpy will be opposite of this negative value. It'll be a positive value. Okay, so I'm going to do that first, and then once I do this, I think you'll understand what I'm getting at. Okay, you can see what I did here is I took this reaction with the diamond and I reversed the reaction. Okay, so instead of CO2 as being the product, now it's the reactant, and I'm taking CO2 and I'm splitting CO2 into oxygen and carbon as a diamond. Now, let's be honest. You can't actually do this, but mathematically you can. Okay, mathematically you can do that, and if you do that mathematically, then you can change this negative, this loss of energy to a gain of energy. Okay, so the negative becomes a positive. All right, and then I can take this reaction. I'm going to rewrite it down here, and you'll see what I've got in a second. Okay, so I've rewritten the graphite plus oxygen reaction. So now the reactions are both together, and you can see that I'm going to add those reactions together. I'm now going to sum up these two reactions, and I'm going to write everything out, and you'll see what we've got. All right, you can see what I've got now. I added both of these reactions together, and then I wrote all of the reactants and products down here. Okay, you might immediately notice that some of these things are going to cancel out, right? On both sides of the equation, I've got CO2. On both sides of the equation, I've got oxygen. And what I'm left with here is graphite and diamond. Graphite, C, graphite makes C, diamond. Okay, and now what I'm going to do is I'm going to add these two enthalpies. Okay, I added all of the products and reactants, and now I'm going to add the enthalpies, and we will get this number. Okay, this is the change in the enthalpy. It is minus 1.9 kilojoules, and that's the answer. Okay, so how much heat does it take to take 1 mole of graphite to create 1 mole of diamond? It takes, it's actually a positive, I'm sorry. It requires 1.9 kilojoules. All right, we're going to try another one. Okay, so here comes our next sample problem. All right, this is going to be a little bit more involved. The last one was pretty easy, but it was meant to just kind of, introduce you to this concept. Okay, so here we are. First thing I want to mention is that you're really going to want to start paying attention to the states of matter. The states of matter aren't going to play into this particular problem all that much, but sometimes they will, all right? So I want to really warn you, and like I've said many, many times before, you always want to be paying attention to things like units and some things that you might otherwise think as extraneous, like states of matter, things like that. Really be paying attention to those things now, okay? So, anyway, this is the reaction that we are going to work with next, and we are going to try to find the change in enthalpy. All right, so I'm going to write down what is known. All right, so let's assume that we went to some handbook or something like that and found some reactions with known enthalpy changes. All right, I'm going to write those down right now. All right, so these are the reactions that we're going to work with. Now, you're going to notice something here that you've never seen before. For this coefficient here, they've written it as 3 halves instead of like a whole number that you're used to seeing. Like in this next equation, you got a 2 and a 1 and a 2. Well, here it's got 3 halves. Why the heck are we doing that? Okay, here's the reason. Okay, it's actually simplifying things for us, because when you write the coefficient like this, then you're looking at just one sulfur combining with oxygen to form one sulfur trioxide. Okay, so that one sulfur, in order to turn into sulfur trioxide, is going to take this amount of energy. 2 moles of sulfur dioxide combines with oxygen to make sulfur trioxide, and that is going to give off this amount of energy. Okay, please don't let these weird coefficients throw you off. They're just numbers. It's not a big deal. Okay, but now we're going to take this information and we're going to sum these reactions, and we're going to get this reaction and see what is the calculated change in enthalpy. Okay? All right. First off is this. All right. This reaction is my goal. Okay? Sulfur's a reactant, oxygen is reactant, and SO2 is the product. Okay, now, in this second reaction, SO2 is a reactant. So in order to make this reaction, in order for this reaction to have SO2 as a product, we're going to reverse this reaction. All right, so I'm going to do that right now. I'm going to just start by reversing this reaction. Okay, so I just reversed this. And I know that this is the form of this reaction that I want to use from now on. To reduce any confusion, I am just going to cross this out. We've used it. We're not going to use it again. Okay? That leaves us with these 2 reactions that we're going to sum up. Now, here's another problem. Okay? In this reaction, I have 1 SO3 as a coefficient, and here I have 2 SO3s as a coefficient. When I sum up these reactions, I want the SO3s to cancel out. So I'm going to take this reaction and I'm going to divide everything by 2 in order to get 1 and 1, and this is going to be 1/2 for the oxygen. All right, I'm going to do that right now. Okay, so I divided everything by 2. You can see that this is divided by 2, okay, to make 99.1 kilojoules. Also, please see what I'm doing here. I mean, really, let's be really explicit about the sign, okay? I'm just going to say, don't be lazy. Just write everything down. Otherwise, you might get confused. You might get lost. Okay, what did I do? How did I get here? Okay, in order to keep things organized, I'm going to do this right now. Okay. Since I've already divided this reaction by 2 and I don't want to use that anymore, I'm going to cross it out. I don't want to be confused by too many things on my page, but I am now ready to use these 2 reactions to sum up to get this final reaction. I'm going to rewrite everything so that it's easier to see. Okay, so I rewrote everything in red. I want to separate what we did before to what we're doing now so that it's easier to see. Okay, so now I'm going to sum up these reactions. And rather than write everything out like I did before, let's just take a look at this together. I've got SO3 on both sides of the reaction. So I'm going to cancel those out. Okay. I've got one sulfur. I'm going to write that down here in the sum. What about the oxygens? So I'm going to take 3 halves minus 1 half. And that's going to give me 2 halves, which, by the way, is 1. So I'm going to write that down as O2. Okay. And let's be consistent here. I'm going to, I'll cross those out because we did the math, and that'll set that aside. And then we've made SO2. So after the arrow, SO2. This was our goal reaction. This is what we were, going for. And now all we have to do is add these two numbers, all right? I'm going to add a negative 395.2 plus 99.1. All right, so if I add those numbers together, I get a negative 296.1 kilojoules. Now, I could do another one on this video, but I think to keep the video shorter, I'm just going to stop here. And before I go, I really want to emphasize just how important practice is going to be with this. Because when you just look at all of this, it's going to look crazy, okay? You have to be involved in doing this and sorting it out in your own mind. One of the reasons I made this video is so that you can stop at any time, replay at any time, and if something you don't understand, you can replay it and try it again, okay? Again, you're really going to need to work with some practice problems, and I will provide you with those, all right? I will probably make another video just solving a couple more of these. So anyway, good luck, everyone. I'll see you later.